Okay, let's go through an illustration to understand how TLBs work. So I'm also going to use this opportunity to illustrate how a process is created by the operating system and how it begins its execution. So when an operating system is asked to create a process, as part of that creation step, it would create a fresh page table for that process. And that page table would be initialized to all invalid entries, except for few entries that correspond to the instruction segment and the global data segment in the address space. So those pages would have pointers initialized to point to the corresponding data and instructions in the executable, which is stored on the disk. And we will see how that is done very soon. And then the process will be scheduled on the processor. The program counter will be initialized to the first instruction, and then the instructions will start executing. So now let's see how all this is stored in memory. All right, so now before the operating system starts a program, everything looks empty, except for on the disk, you have let me bring my pointer here. So except on the disk, you have the executable that is stored. So here I'm assuming that my executable is stored in three different pages. Text 1 and text 2 correspond to the instructions, and global data corresponds to the global data segment of that particular program. Okay. Now let me explain all these different tables briefly so that you can follow the example. So of course, this is the disk pages colored in blue, goes from the address D0 to D1003. Now this page again could be increased or decreased based on the user. It's a swap partition size. And it can also include non-swap partition if it comes to the data such as executable files, which is the case for this text and global data. All right, so the pink colored box represents the main memory. So this is your physical DRAM. I have 4 pages worth of space. And my yellow box is the TLB. This is the structure that we just talked about. It is a cache for page tables. And because it's a cache, it's located within a processor. So memory is located outside the processor. Disk is obviously also located outside the processor. But TLB is a very fast structure that is located within a processor, and it has only very few entries. So in this example, I'm assuming 2. Each entry is a very simple data item. So this is a virtual page number and a physical page number. So it's not a lot of information here. It's just a few bytes worth of data. Whereas these contain 1 page worth of data. So these boxes are not to scale. And so disk page is also 1 page worth of data. So typically this is 4 kilobytes. This is 4 kilobytes. And here we are talking about less than 4 bytes. So these are physical structures. TLB, main memory, disk pages. These are all physical structures that is located somewhere in your computer system. The ones that you see here, these are not physical structures. They are just, for example, the page table is a logical data structure that an operating system has allocated for this particular process. And the page table, being a data structure by itself, is going to be stored somewhere in the physical memory. And this references, it's an example that I'm going to use for illustrating how this whole system works. And the physical references is the reference or the address that I would get after translating these virtual addresses into physical addresses. So these are virtual addresses that are generated by the program when it executes in your pipeline. All right. Now I'm going to also assume that the page size is 4 kilobytes and the page table entry size is 4 bytes, which is not going to be super important for this example. But it's important to understand that we need 12 bits for the page offset, because when you do the bit manipulation, that information is going to be needed. All right, so the very first step, when a program is loaded in memory, the first thing that the operating system, or one of the first things it does, is create a page table for this process. And like I said, the page table is going to be stored somewhere in memory. So in this example, I'm going to assume it is stored in M0. This one page is reserved for storing the page table of the process that the operating system just created. And like we talked about, the operating system initializes the entries that correspond to the instruction and the data segment, which are located in the executable when you start the process. So what D1000 says is my virtual page 0 is an instruction segments page, and it is located on the disk, which is text 1. And I'm going to mark it as read only because I don't want my program to change my instructions. This could be different for self-modifying code, but for now, this program doesn't change instructions, and so therefore, for extra protection, we have marked it as read only. The second page, page number 1, virtual page number 1, is also a text segment. Again, it is stored on the disk. A pointer to it is stored in the page table. And the third page is the second, with virtual page number 2, corresponds to a global data segment. So if you go back to one of the earlier lectures in this course, we talked about how a program's address space is composed of instruction segment, data segment, and then dynamically created heap and stack. So what operating system has done for us is it has created all the instruction and the data segment, but of course it has not created the heap and the stack, which would be created on demand as the program executes. Now, let's say the program starts its execution. The very first thing that will happen is the first instruction needs to be fetched. So the address, let's say the operating system has initialized the program counter to 0. So now instruction has to be fetched, and that requires an address translation. So you would go and check the TLB. So the processor in the fetch stage would check the TLB for an address translation. The translation says, well, the TLB is empty, so it's going to be a TLB miss. So now the TLB miss handler would look up the page table, which is stored in M0 of the main memory. So this is a main memory lookup. Again, we are in the middle of an instruction fetch here. Because of the TLB miss, we have to do a main memory lookup. And that main memory lookup would allow us to do the address translation. And the address translation says, well, the instruction is located on the disk. So it's going to be a page fault. So I accessed the physical address 0 to do the address translation. Remember, 0 corresponds to this page 0 here, which stores the page table, and I access this address 0 to do the address translation, and I discover that it's a page fault. And so now I have to access D1000. And I access D1000 and I bring the data into the memory because I have free memory pages. So operating system allocates a new page, M1, and then changes the page table entry to reflect that fact. And now I would also want to cache this in the TLB so that in the future, if I were to access the same page, I don't need to go through this TLB miss handler that would require me to access the page table in the main memory. Okay. So now let's say that now that I have loaded the text 1 into my main memory, now I can service the original instruction fetch by accessing the main memory. So the main memory physical address would be 1, which is the most significant hexadecimal digit, followed by the page offset for this is going to be all zeros. Remember, our page size is 4 kilobytes, which is 12 bits for the page offset, which translates to 3 hexadecimal digits. So the page offset comes from the last 3 hexadecimal digits from the virtual address, and I have that same thing here. So you need to convert it all into binary format and then concatenate the page offset to the physical address page number to get the full physical address. And in this case, I'm able to do that very easily because my 3 last hexadecimal digits need to be concatenated with this. So it's easy for me to just work in the hexadecimal space for this example. All right, so now I got my physical page number 1 because that's where my text 1 got stored in. So virtual page number 0 is being translated into physical page number 1, and that is what I have cached here too. Virtual page number 1 is translated to physical page number 1. All right, so now let's go and execute the next instruction. So the next instruction, the PC would have been incremented by 4, and so I'm accessing the next instruction, which is 004. And because we had already done the hard work of bringing the text page and doing the address translation and caching it in the TLB, we don't have to go through all that again. The TLB has the address translation for us. It says 0 page number has to be translated into physical page number 1, and then we can slap the offset to the end, and then we get the full physical page number, which is 1004. And so this is not a page fault because again we have brought the page to the main memory before, and the corresponding address 1004 would be accessed, and then you can go on from there. Now I'm ignoring the processor caches in this whole picture, but if you did have a processor cache, then address 0 and 4 would be part of the same cache block, most likely, because block sizes are larger than 4 bytes, and so it would have also been a cache hit. But we are ignoring that detail now because our focus is to simply understand how the TLBs and the page tables work. Okay, so now let's say assume that this second instruction is some form of a memory instruction. It could be a load or a store, we don't care for this example. And what that means is that it would generate a virtual address as part of that load or a store, and that address need to be accessed, the memory has to be accessed in the memory stage of that instruction. And so that address happens to be, the virtual address happens to be this 7FFC. Of course, there's no entry for that in the TLB. The virtual page number 7 does not exist in the TLB, so it'll be another TLB miss. So this is our second TLB miss. And in this case, it's going to be slightly different from how we handled the first one, because if you look at the page table entry for the virtual page number 7, there is no map. So unlike the first TLB miss where we did have a pointer to the disk, meaning the data existed before, even though it was a page fault, the data existed on the disk. This page fault is different because the data doesn't exist at all. This is the first time the process is interested in this page and no data has been created for it. Okay, so maybe this is a store instruction that is trying to store data into this new address that has never been accessed before. All right, so what does the operating system do? The operating system says, oh, well, this is a no map. Fine, I will allocate a fresh new virtual page for you, physical page for you. And let me say that page happens to be M2. And then from that point onwards, it works as in the case of the previous page fault, where M2 is allocated a fresh page, and the translation for that page is stored in the TLB. So 7 translates to 2 in the physical address, and then the physical address 2 followed by the page offset is going to be accessed. Now, one detail that I missed is when the operating system creates a fresh page for a no map entry, there is no data to start with, so it has to initialize it to something, and typically they would initialize it to all zeros. Okay. The other bit that is different about this page is that it has read and write permission. That's why it's R and W. Previously, because it was an instruction page, we had it set to read only, meaning we didn't want the instructions to be modified. Okay, so now let's go and execute the third instruction. Again, now it's going to be the instruction fetch that increments the PC by 4 from 4 to 8, access the TLB. Each page is of size 4 kilobytes, so this instruction would be part of that same page, so it's a TLB hit, and we go through the same process like we did before, where we go and get the instruction. That's no different. Now let's assume that this instruction is also either a load or a store instruction, and in this case the address is different from the previous addresses. Not only that, it's to a virtual page that is different from all the previously accessed virtual page. So before we had access to virtual page 0 and 7, and this one is going to be to 2, which we don't have in the TLB, and it's going to be a miss. What do? Well, the same as what we did before, which is to go to the page table and check whether there is an entry. Well, in this case, even though this is a data access, there is an entry for it, and it's on the disk. So it is a page fault, but this page fault would require that I go and access the global data segment, and then the global data segment would be brought back into the main memory, and then a corresponding entry would be allocated in the TLB as well. So remember that our TLB was full, and so we had to find, let me go back to the previous slide. So before I had 0 and 7, now I'm bringing in a new entry. I don't have space for it, so I have to evict one of these two entries. I've been accessing 0 a lot, so that's clearly not released recently used entry, because we just accessed a 0 entry, right, for the instruction. So according to LRU, I would have to evict the virtual page number 7's entry and replace it with the one that I just accessed. And then this was accessed, allocated to the physical page number 3. So 3 followed by page offset is my physical address that I